This particular video, we're going to take another look at another theory for how molecules get formed. It's known as molecular orbital theory, oftentimes referred to as MO. In molecular orbital theory, there's several guidelines we'll follow. The first of these is that the number of molecular orbitals is equal to the number of atomic orbitals that are combined in forming the molecule in question. Now, when we refer to atomic orbitals, that's when we have the things such as our 1s, 2s, 2p, etc. Those are all atomic orbitals. Our second point for molecular orbitals is that molecular orbitals, as with atomic orbitals, are arranged in order of increasing energy, lowest energy to highest energy. The third point is that our valence electrons, they get distributed amongst the molecular orbitals, the same as we would do with atomic orbitals. In that when working with molecular orbitals, we still have a capacity of 2 electrons per orbital. Lowest energy orbitals fill first, so we still follow the off-ball principle. And then lastly, when we fill up electrons in the orbitals, we go one at a time before we double up in orbitals that are of comparable energy, which is we still follow Hund's rule when working with molecular orbitals, just as we did with atomic orbitals. Let's take a look at how hydrogen atoms and molecules, we take H's to make H2. It's our simplest example to get a look at molecular orbital theory. Looking at our hydrogen atoms, each hydrogen has a 1s1 electron configuration. This indicates that each hydrogen atom has a single 1s atomic orbital, which gives us a total of 2 atomic orbitals as we prepare to make an H2 molecule. In molecular orbital theory, the number of atomic orbitals that we have adds up to give us how many molecular orbitals will get formed. Since H has 2 atomic orbitals, we're going to form 2 molecular orbitals as we move forward to make our H2 molecule. Here's the beginnings of our picture. We have our 1s atomic orbital from one H atom, and we have our 1s atomic orbital from the second H atom. The 2 atomic orbitals combine to make what's in the center here. We have our 2 new, what would be referred to as our 2 molecular orbitals that have been formed by the combination of the 2 atomic orbitals of our hydrogen atoms coming together to form an H2 molecule. In our picture, the lower energy molecular orbital is referred to as a bonding molecular orbital. We form one bonding molecular orbital that's of lower energy than the original atomic orbitals. Our bonding orbital that we have here is of low energy, and it's considered to be stable because it is at lower energy than the original atomic orbitals. The designation we have here is sigma 1s for this bonding orbital. The second molecular orbital it forms is a single, what's called anti-bonding orbital. The anti-bonding orbital is higher in energy than the atomic orbital from which it was formed. The anti-bonding molecular orbital at a higher energy is then considered to be unstable. The anti-bonding molecular orbital is designated by the sigma 1s with the little symbol of an asterisk. The little asterisk symbol will designate molecular orbitals as being anti-bonding orbitals. Now, if we look at our hydrogen atoms, each hydrogen atom has a single 1s electron drawn in its atomic orbital right now. Following the off-ball principle, the lowest energy orbitals fill first. So our bonding orbital now has a pair of electrons in it. The anti-bonding orbital has no electrons in it. If we take a look at a bonding orbital, we would observe that there's going to be a very high electron density from the pair of electrons that are located between the 2 nuclei in the bond. Looking at our bonding pair of electrons, When the pair of electrons is isolated between the two nuclei or held onto by the two sets of protons, the overall energy drops compared to the two separate atoms, making the bond a more stable and favorable arrangement than the atoms separate from one another. Now, in contrast to a bonding orbital, when we have an anti-bonding orbital, there's actually no or zero amount of electron density between the two bonding nuclei. In our depiction of this, the anti-bonding orbitals actually face away from the bonding atoms. And we can see right in this area between the atoms, there's zero electron density that would occur with our anti-bonding orbitals. This area is often referred to as a node, or a region where we have no electron density. What occurs in this situation then is because we have no electron density between the nuclei, the positive charge of the nuclei are then less shielded from one another. What we have then is, with the positives of the two nuclei not being shielded from one another, there's a lot of positive repulsion then between the two nuclei. Because this is high, we end up getting a destabilizing effect on the bond. In other words, it's at a much higher energy than the bonding orbital is. Let's take a moment and return to our orbital diagram for the formation of our H2 molecule. Now we have something where the number of bonds that are going to form in our molecule is also equal to something known as the bond order. And the number of bonds or bond order is given by this equation. We have B minus AB divided by 2. Where the B represents the number of electrons that we have that are in bonding orbitals, and AB represents the number of electrons that we have that are in anti-bonding orbitals in our molecular orbital diagram. Doing the calculation for our H2 molecule, we have 2 bonding electrons that we see here. We have 0 anti-bonding electrons. Divide by 2, and it gives us 1. That tells us in an H2 molecule we would expect to find a single bond, which we know to be the case for an H2 molecule. It's H with a single bond to another H. So our molecular orbital theory verifies our H2 molecular structure. Let's now repeat the process for something different and see how it works for an He2 molecule. If we look at an He atom, its electron configuration is 1s2, giving us 2 electrons in the 1s and 2 electrons in the other 1s for our atomic orbitals. Distributing the 4 valence electrons, we have 2 that fill the lowest energy orbital first, our bonding 1s orbital. The remaining 2 go to the next highest open orbital, which is the anti-bonding orbital, molecular orbital. Calculating our bond order for the He2 molecule, we have 2 bonding electrons, we have 2 anti-bonding electrons, divide by 2, and that gives us a bond order of 0. The bond order of 0 means we have 0 bonds that form in this structure due to the destabilizing effect of the anti-bonding pair of electrons, and we end up with no molecule, which we know to be true that He, helium, a noble gas, does not form any compounds or molecules, and there's not any He2 molecules that exist. Let's take a moment and revisit the p atomic orbitals that exist at energy level 2. If we recall with the p orbitals, there's 3 p orbitals, one oriented along the x-axis, one oriented along the y-axis, and one along the z-axis, but they all have an identical shape. Let's first focus on the 2px of the p clouds. It's oriented along the x-axis. If we have a couple p along the x-axis atomic orbitals going to molecular orbitals, along the x-axis, they're going to overlap right along the bond axis. So here we have the overlap of our p clouds, And because they're overlapping along the bond axis, this would be designated as a sigma bond. However, if we look at the 2p y orbital, it's along the y-axis, and the 2pz is along the z-axis, both of which are perpendicular to the bonding axis. However, with either the pz or pyp orbitals, which are perpendicular to the axis, the overlap we get is from the edges of the clouds above and below the bond axis. And this type of overlap ends up making not a sigma bond, but we end up getting a pi bond created by this type of p atomic orbital overlap when they're going into molecular orbitals. Next, let's just take a real quick peek at what a molecular orbital diagram would look like when our valence electrons aren't at energy level 1, but when we move up to energy level 2. Taking a look at our picture, we have the 2s, both bonding and anti-bonding orbitals. Then we have the 2p bonding orbitals for both pi and sigma types of bonds. And then we have the 2p anti-bonding orbitals for both pi and sigma types of bonds with the p clouds. Let's do a quick example and do something such as N2. N2 has 10 valence electrons. The first 4 electrons go into our bonding and anti-bonding 2s molecular orbitals because these are lowest in energy. The next 6 electrons go into our pi 2p and sigma 2p bonding orbitals. This accounts for all 10 now of our valence electrons in N2. Using our formula to get the number of bonds, we have 2, 4, 6, 8 bonding electrons, and we only have 2 anti-bonding electrons. 8 minus 2 divided by 2, that gives us 3. A bond order of 3 means that we have a triple bond in our N2 molecule, which is the case. And that when we do a Lewis structure for N2, we come up with this structure. And our molecular orbital theories has predicted we should have 3 bonds between our 2 N atoms, giving us a triple bond in our N2 molecule, which is stable and does exist.